I'd like to introduce Dr. James Fergusson, and he is at the Center for Theoretical Cosmology and the Deputy Director of the Center for Doctoral Training in Data Intensive Science at the Stephen Hawking Center for Theoretical Cosmology. That is a mouthful at the University of Cambridge. So I'd like to welcome him to the stage. Thank you very much. Thanks, James.
Thank you very much for the introduction. So it's really exciting to be here to be able to tell you about what we're doing in Cambridge. First, I'm going to talk about the kind of things that sort of give you a background of cosmology and the kind of problems we face and the kind of challenges that we have to overcome to get information and to understand our universe. And I'm also then going to show at the end some of the key things we're doing in Cambridge and some of the cool sort of simulations that we're doing. So first up, let's tell you all of cosmology in 2 minutes. So it starts off at the beginning. It starts off with something called inflation. This is a part where the universe expands exponentially quickly. So when I say inflation, it sounds a bit like you're blowing up a balloon or something, or inflation in the economy where the economy grows a few % every year. But we mean something much, much more extreme. We mean something that essentially the fabric of space and time is stretching at an exponential rate. And so actually in only 10 to the 32 of a second, you imagine if you were trying to blow up a balloon, if you started with a balloon that was a centimeter big, in that 10 to the minus 32 of a second, which is a million billionth less than it takes a photon to travel the width of an atom, that balloon would have to be 1 billion light years across. So it's really one of the most extreme events you could possibly imagine. And so what it does is it stretches the universe out. It makes it very, very flat. It wipes out any information of what was beforehand. And so that really puts a sort of a wall on what we can study. It makes the universe perfectly flat, but not completely perfectly flat, because it's so extreme that it'll actually take these little quantum perturbations that you have, happening everywhere all the time. They sort of get caught out by this extreme event, and they get stretched out to be the size of sort of galactic scales. And these tiny perturbations of the density, and then will they grow over time, all the way as you go along, as to gravity. If something's slightly more stuff in one place, it just pulls stuff towards it, gets bigger and bigger, and eventually forms galaxies and stars and all the things we see today. So there's one other thing that's worth talking about, and that's, you can see a little slice in the middle, just there, with blue and red dots, and that's the cosmic microwave background. And so that's one of the most important data sets we have in cosmology. Essentially what happens is at the very early part of the universe, it's very hot, because the universe is quite small still, and all the electrons are free, so it's like a plasma. And just like on a foggy day, the light can't get anywhere because it keeps bouncing off droplets of water, the light can't go anywhere in the early universe because it keeps bouncing off free electrons. And what happens is the universe expands and it cools down, and there's a particular time, 380,000 years after the Big Bang, when suddenly it's cold enough that atoms can form. The electrons bind into the protons, make hydrogen, and suddenly the light's free, and it can free stream out. And so this is the moment where the fog clears, the universe becomes transparent. And so when we look in the sky and we look out, if we look, the furthest thing we can see is this cosmic microwave background, the moment the universe became transparent. And so if you imagine the universe was a person, it was 100 years old today, then the cosmic microwave background essentially is a baby photo for when it was 1 day old. So it's the earliest information we possibly have. Okay. So we can describe all of that, amazingly, in 6 parameters, the standard cosmological model that we arrived at sort of recently, maybe 10 years ago, it started to be the accepted thing. There's 2 parameters that do the initial conditions, the average size, the density perturbations we get from inflation, and whether they're slightly bigger on larger scales or smaller scales. We have 3 to describe the stuff in our universe. We have some normal stuff that we're made of, atoms and things like that. We have dark matter, which is matter that doesn't interact with light. We know that it exists from galaxy rotation curves. We have no idea what it is. We also have there's something called dark energy, which is a very mysterious and strange thing. It has to be there just from looking at the geometry of the universe and looking at distant supernova accelerating away from us. But we really have no idea what that is. And the last parameter is simply the time, where we are in this model. So we have a model that sets up a particular evolution, and we just need to know exactly where we are. So the one troubling thing about our model is it's very beautiful, it works wonderfully, it works to sort of percent level for most things, is that we don't actually know what drives inflation, we don't know what dark matter is, we don't know what dark energy is. So we only understand 5% of it. But we've given it names, so that's close enough. So most of the research we're doing is now trying to work out what driving inflation, what dark matter could be, and trying to get some understanding of dark energy. So The reason we have this model is essentially we've had a real revolution in cosmology. Over the last 20 years, we've sort of had an exponential growth in the data that's accessible to us. So I'll take you on a little tour of how that's changed. So this is back in 1998, 1999. The key paper in cosmology, the most important thing, was from a high-Z supernova team, measuring supernovas at a long way away. They studied 16 supernovae, so 16 data points. Enough that you could sort of name them, you could make friends with them, you could understand them all very, very well. And this was enough to prove that dark energy existed. We didn't really know how much, we just knew that it couldn't be zero. Right? And so that was the status of cosmology. It was a very thing, you could sort of almost do it on paper. You didn't have to get exact numbers, as long as you sort of, it's a yes or no, if something exists, factor of 10, it's the same as 1. But then in 2000, we started to get more professional. We got things like the Sloan Digital Sky Survey. So that sits there, and it's just trying to scan every galaxy in the universe, trying to measure its position, where it is, how far away it is. And so it's quite an amazing experiment. They take a picture of the sky, they work out where all the galaxies are, then they get a big metal plate, and they drill a hole everywhere they think a galaxy is. They put a fiber optic cable in the hole, they put it back, and they point it at the same point of the sky. And each fiber optic cable then takes a very detailed measure of that particular galaxy. So it's been going for 19 years. It's had lots and lots of upgrades. It's now collects about 200 gigabytes of data a night. And the full data set's just over 100 terabytes. But it sort of had to grow there quite slowly. So that was the first time we sort of became very professional and sort of doing a full survey of everything. Before, we just looked at particular objects, particular things we could buy some time in a telescope to look at. The next big revolution was when we looked at the cosmic microwave background. So this was WMAP in 2003 it started. It has about 3 million pixels, and it's measuring this light all around it. You can see sort of a map of it there. And this was the time when we actually could say, now we have a cosmological model. That sort of confirmed that we definitely have roughly 5% matter, roughly a quarter dark matter, and then the other rest of it, 70-odd%, is dark energy. We did that again, 16 times the resolution with Planck, which is the experiment I'm involved in. And this one, measuring the CMB, it's about 4 terabytes, the data set, 150 million pixels for a map. And this one gave us the cosmological parameters to 1%. So we've moved from a thing where we were wondering whether things existed or not to knowing their value to 1%. The next great experiment that came along was Gaia. So this is trying to map out the position of every star, comet, planet, object that you can see in the Milky Way and tell you exactly where it is. So it's an incredible experiment. It sits in space, and it's used mostly just to map all these things out, is get the position, the velocity of every object. It has incredible resolution. The reason the data sets are so big is the experiments we have are incredible. This one can resolve a single human hair at 600 miles away. That's its angular resolution. So if you put it on the roof here and you pointed it at Vegas, you could count the hairs on people's heads. And that's all done actually with software. Using that, it takes a picture from one side of the Earth, goes to the other side of the sun, takes another picture, and uses the parallax to get the object's position very, very accurately. And so this one's, in only a few years, has managed to get to the 100 terabytes of data. And so that's about where we are now. We're sitting on these amazing data sets. We've got this great model. We've got something like hundreds of terabytes to deal with, so it's quite big. 100 terabytes isn't the end of the world. I mean, people in here, I'm sure, have dealt with data sets of similar sizes. But in a year or two, things are going to get a lot worse. We start off with LSST. So this is like the new version of SDSS, the Large Synoptic Survey Telescope. It's basically just a big camera. It takes pictures. It's going to do 20 terabytes a night for 10 years. The final data set will be about 500 petabytes. If that sounds bad, wait till you hear about this one. So this is the Square Kilometre Array. This is going to be a network of telescopes in South Africa, about 1,300, I think, there, eventually 200 initial phase, and then going to be 1 million radio antenna in the Australian outback. First phase is like 130,000. Those radio antenna in Australia are going to generate 157 terabytes every second. And so that's going to be around 5 zettabytes a year, which is 3 times more than all of the available storage in all data centers in the world. And so this is the thing, we're now getting data that's not even possible to store. It's not about processing it, it's about simply getting it so you can actually put it somewhere to look at later. So this one has on-the-fly processing at the thing to reduce it down to maybe 7 or 8 terabytes a second. Then has to go to a supercomputer a long way away, so the radio from the supercomputers don't interfere with the experiment. And we're going to need 250 petaflops running continuously to take this data and turn it into 18 petabyte sky cubes that we can then save. All right. So that's sort of where cosmology is at. We have very, very big data, and it's going to be a lot of problem trying to analyze it, but we've actually needed HPC for a long time. It's not really the data size that's our problem. It's the thing that we sort of say to everyone because it sounds very impressive, but really, there's a lot of reasons why HPC is very important. It's part of it's the operations we want to do, and the other part we'll get to in a bit. So what we want to do is we want to constrain parameters. We do it by just looking at the density of the universe. That's all we really ever look at. You imagine it's just like the surface of the ocean. We just want to see if it's slightly more dense here, slightly less dense here, or a wave slightly higher, slightly lower. And so all we do is we just measure these, we're interested in the statistics of it. So we say, how big is a swell, long wavelength mode? It's usually 5 meters or something like that. And how big is a wave? That's got a shorter wavelength, maybe they're about 1 meter. And then you have to put some ripples on there. They're only a few centimeters big. And that would be enough to draw that picture that you can see up there to some reasonable accuracy. And then so that's what we do. We take something like that picture, we draw something that's called a power spectrum, which essentially is just the variance on each scale. And then from that, we can find out all our parameters. So while the first one, you'd say the swells are bigger than the waves, are bigger than the ripples. Here's the CMB, and this is the power spectrum you get from it. And you can sort of look at it, you can convince yourself there's a big peak around 1 degree. And this is the sound horizon at the time the CMB become decoupled. And you can sort of look at the picture and imagine that you can see 1 degree sized dots. So let's look at a case study of why we need supercomputing and why everything's so difficult in cosmology. We start out with 4 terabytes of data on the time stream. We do some map reconstruction and cleaning to turn it into like a little picture of the sky. The next thing we do is we then take these maps to tens of gigabytes, not very big, do harmonic transforms, such as a spherical version of a Fourier transform, and we add them together in an optimal way, and then we calculate power spectra. Once we have power spectra, we then do nested sampling to find the maximum likelihood fit of the parameters, and that's not too bad. Also, if anyone here is still using MCMC, you should think about nested sampling. It's not known much outside of cosmology, but it's much, much better. So this took 100 million CPU hours in Planck. And the question is, why on earth do we need 100 million CPU hours to process 4 terabytes? And the answer comes from the most fundamental problem we have in cosmology. So this is a little children's poster of a scientific method. You come up with a question, you make a hypothesis, you do an experiment, you collect the data, analyze it, write a report. So for medicine, it's like, I want to treat a particular disease, I find a drug, I do an experiment, a big trial, lots of patients, I look at the reduction in symptoms, I do some stats, I write a paper. Great. In cosmology, the problem is a bit different. We come and we say, well, the question is, how does the universe work? Our hypothesis is that it's GR, general relativity, it's got some dark matter and energy, it's got some normal atoms. The problem is we can never do an experiment. We can't rerun the universe. We can only look at it. And we only have one. That's the other problem. At least if we were studying stars, we could look at lots of different stars. We can only look at one universe. So all we do is we just take pictures of it. We just take photos with our cameras, big telescopes, pictures, 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 pictures. Then we've got the question, how do we do errors? How do we really see if our universe is just in a statistically unlikely place, but the theory is correct, or whether something unusual is happening? And so it's very difficult. And so the solution to this is we have to simulate everything. And so we firstly, this is the Planck pipeline for simulations. This is the thing that took 100 million hours. We simulate the universe. Once we've got a picture of the universe, that gives us the CMB. We then simulate all the foregrounds, the galaxies, the point sources, all the planets, zodiacal light, things like that again. And then we have to simulate the experiment measuring that universe we've simulated. So then we take our experiment, we say it's going to have a beam, it's going to have sideways pointing, it's going to have glitches, it's going to have nonlinear gain, thermal fluctuations, problems with the cooler. And we have to simulate all of that, and then we have to run our pipeline at the end of that simulation and see if we get something that looks like the data we've got. And so that this only 4 petabytes of data has to be done thousands of times. So the 4 terabytes becomes petabytes, and the simulations makes a nice loop, and we just have to go round and round and round until we get everything that comes out nice. And so even small data sets like Planck, that's only really a few terabytes, mostly gigabytes once you process it, can be very, very challenging. And success in cosmology can largely depend on what kind of computational performance you can access. And because it's a very competitive field, and if you can't process the data and get the answers fast enough, someone else will do it for you. Right, so we're going to get into some examples that we do in my department, the Department of Applied Maths and Theoretical Physics at the Center for Theoretical Cosmology. So the first one's my one. We're really interested in the parts of theory, right? We want to know what data sets will give us insights into theoretical breakthroughs. We're not interested in just getting parameters better. We want to see if there's paradigm shifts or things we can really see that are new and give us new insights. So my one is working on higher order correlation functions. We do the power spectrum is the common thing to do. That describes the free behavior of a field. So if we look at inflation, we look at the power spectrum, it tells us how that particular one field works when it's completely by itself. So I look at the higher order correlation. So I look at the 3-point function, the exponent up, the bispectrum, which is like an unpacked version of the skewness, where you get a normal bell curve and you just lean it over a bit to one side. And this describes the interactions between that inflation field and all of the other fields in the standard model that we have. The problem with it is it's quite expensive. So our naive estimation is about 10 to the 66 calculations to work this out. And my work's been sort of trying to compress that down to something that's solvable in a way that it will work in general for any model. And so we managed to do this in the Planck satellite. We had lots of help from Intel. Eventually, we got one of their, John Pennycook, one of their programmers to come and help us. They heavily optimized some of the analysis pipeline they did to work on KNCs and KNLs. And that resulted in the 2015 HPR award for high performance data analytics. Managed to get 8,000 times faster, which is very good, but a little embarrassing for me that it was quite that bad to begin with. It also needs a huge amount of memory to run efficiently. It's about 1.5 terabytes. And if you're not on a shared memory machine, like the Superdome Flex or something, then it will run much, much slower, because essentially you're trying to take every point to every point to every other point. And you do that very, very fast. So you need to be able to see all the data on every node. And then we also got some more help from Intel. This was Johannes Gunther, helped us visualize it. And so this was another great breakthrough in that what we were doing beforehand was us taking model, comparing it to the data, seeing if it fits. It didn't fit, get another model. I went through about 30,000, every model in the literature. But then when we could visualize it properly using the power view, then you can look at it and you can say, oh, okay, it's obvious now, these models will never work because their picture's just different. And these are the models I should look at. So it helps you narrow down that search. So that's a more conventional one. We also look at sort of more exotic things. One of the really interesting ones is cosmic strings. And so these are very strange things. They're topological defects in the universe itself. So essentially what happens, the universe is very hot at the beginning, and it cools down as it expands. And just like ice or water goes through phase transition, starts out at steam, condenses down to water, and then it will eventually freeze to ice. The universe essentially does the same thing. And just like when you go from water to ice, you can imagine water freezes. In this particular location, the ice crystals start pointing this way, and they slowly expand out. Everything aligns with them. Maybe at this point over here, they start pointing that way. And as they grow out and meet each other, there's a point where they can't match up, and you get a defect. And that's what you can see in this picture, right? All these lines, part of them are cracks, but they're cracking along bits where the ice crystals are mismatched, and it's weaker. And so you get these defects. And here we can get them essentially in the fabric of the universe. They're parts that can't condense when you have a phase transition. And so this will tell us a lot about the structure of the high energy theory. They're very, very difficult things to work with. The problem with them, and trying to do simulations of them, is that they're very, very long, they're very, very thin, they're very, very heavy, and they're very, very fast. So you need to have full relativistic corrections. You need to worry about all the field theories. And you need to have a highly adaptive mesh that can cope with the fact that they want to have lots and lots of small cells near them, but the small cells want to be thin but long so they can follow the string. And so this is a simulation of a big network. So imagine the universe is frozen. This network has just appeared after the phase transition. They evolve. The strings move relativistically right close to the speed of light. And so they generate all these gravitational waves that come off. They intercute, get little loops. The loops shrink. And so this is something that we could look at in the new LIGO detector. We could look for a sort of a cosmic string background. Can we hear this sort of the noise of this string network evolving? And that would tell us a lot about how the structure of the theory fitted together. So another great visualization with help from Intel, the Carson Brownlee on this one. The last one I'm going to talk to you about is a sort of quite an interesting one here. This is talking about dark matter. So we know that dark matter exists. We know that we can't see it, but it has to be a massive particle. It can't move very fast. And so we look through our theories to find out what could this be? What particles do we have? And light boson particles, this is just a particular particle that's friends with each other like photons, could be the answer. And then the question is, if are they the answer, how do we try and measure them? We can't see them. So the only thing we could do is we could try and hear them through their gravitational waves. And luckily, there are particular types of particles, axions, a few others, that bosonic particles that can actually form boson stars, actually dark stars, if you like. So essentially, there's this whole, it could be this whole universe of little collapsed objects all around, just like our stars and planets and things, but they'd all be dark, we couldn't see them. So this is a picture here of that's a black hole there, and that's a boson star. They're quite small. Black holes are obviously very tiny. Like, kind of imagine like the size of a neutron star. And they sort of held together by part of the bosonic field configuration. They oscillate a little bit. And so they're very expensive to simulate, because you've got to solve all the field equations, you have to solve all of the GR equations as well. And so this is a nice video we've just done. This is going to be over at the booth at Supercomputing, so you can go there and ask lots of difficult questions, like why do they flash and things like that, and see if the Intel people have been paying attention. So this is two of them colliding, and you can see here they are, they're just oscillating very nicely. They get closer, they start to deform, merge into each other, they hit a critical density, and then they collapse. And this is a great gravitational wave, shock wave, sort of going out from this. And this is something we can listen for. And so if you want to listen for this in LIGO, you've got to be able to simulate this process in every possible configuration. You've got to be able to simulate a boson star with a black hole. You've got boson stars coming in at speed, boson stars coming in with particular spin. So you've got to run huge numbers of simulations in every possible environment to build up a template bank of signals that you can then go and look for in the LIGO experiment. And so this is a very expensive thing. We've just started sort of working on this and trying to get these exotic objects in there that we can try and look for. And this would be really, really, really exciting if you could discover something like this, because dark matter is a very mysterious thing. We can't see it. It's very hard to get any information. But this is one way we could get really nice information as to exactly what it is and how it behaves. OK. So that's most of what I wanted to tell you. So the summary, I guess, is that cosmology has finally entered a precision age. It's driven by exponentially increasing data. We've got a very exciting and sort of troubling future ahead. We're going to deal with hundreds of petabytes that we're going to have to find a way to be able to analyze. And that's part of my work as running the PhD program in data science, is that we're now finding that our PhD students, we can't just get them to learn on the fly. We have to get them in and we have to say, you need to sit down and do proper programming courses. You need to learn how to work collaboratively. You need to know how to put version control and unit tests and all this kind of stuff that academics generally don't worry about. Because the data is going to be so much that you're going to need those skills. You're not going to be able to progress without it. And the other problem is obviously we are highly, highly dependent on simulations. And so we're trying to make people more professional in simulation, trying to put much more professional code bases people can use. And also, in an extremely competitive field of cosmology, really if you want to put papers out and be the first to do something, you need to have access to the best cutting-edge computer architectures and also to the support you need to utilize them efficiently. And that's really what helps you make sure you can get the insights and drive the science forward the best. Thank you.